Hello, curious chemists. Did you know some amines can be gases while others are solids or liquids? It's like the carbon chain length throws a surprise party for these molecules. Depending on their size, they change their state. Let's dig in. Lower aliphatic amines, like methylamine and ethylamine, are light enough to be gases at room temperature. As we add more carbons and increase molar mass, these amines become liquids or even solids, sort of like how water turns to ice when it chills out. Primary and secondary amines with up to 3 carbon atoms are water's best buddies. They dissolve easily because they can form hydrogen bonds with water molecules. Picture two dancers holding hands. But tertiary amines miss out on this bonding party since they lack NH bonds, so they're less soluble in water. Aromatic amines like aniline behave differently. They're oily liquids or solids and don't mix well with water but love to dissolve in organic solvents, kind of like a cat that prefers the indoors. Imagine a table showing how the physical state depends on amine type and molecular size. Smaller aliphatic amines are gaseous, medium ones liquid, and big ones solid. This correlation helps chemists predict behavior in labs and industries. So, the physical state of amines isn't random, it's all about their structure and bonding vibes. Ready to heat things up with boiling points? Amines show us an intriguing story about hydrogen bonding and molecular size. Why do amines boil at higher temperatures than similar hydrocarbons or ethers? It's because of NH hydrogen bonds. Think of them as tiny Velcro strips holding molecules together tight, making them work harder to escape as gas. Here's the trend you'll love. Primary amines have the highest boiling points, followed by secondary, and then tertiary amines trail behind. Why? Well, tertiary amines lack those NH bonds, meaning less hydrogen bonding, so they slip into the gas phase more easily. At the same time, larger molecules have stronger London dispersion forces. Imagine more elbow room pushing molecules closer, so increased molecular mass gently nudges boiling points higher. Picture a colorful bar chart comparing boiling points of primary, secondary, and tertiary amines, climbing highest for primary and dipping lowest for tertiary. This combo of hydrogen bonding and molecular heft gives us a clear roadmap for amine boiling points, useful when deciding how to separate or use these chemicals. Hot stuff, indeed. Let's talk about hydrogen bonds, a friendship that really holds molecules together. Primary and secondary amines love to form intermolecular hydrogen bonds, where the positively charged hydrogen on one molecule reaches out to the nitrogen atom on another, like friends lending a helping hand across the room. This NH2N bonding sticks molecules together tightly, boosting boiling points and making them more water-soluble. But tertiary amines don't get this party invite. They lack NH bonds, so they can't bond effectively with themselves. Interestingly, aromatic amines such as aniline behave like secret agents. Some derivatives show intramolecular hydrogen bonding within the same molecule, especially when substituents hang close, changing their physical properties. Imagine a diagram where a primary amine shows clear hydrogen bonds between molecules, but a tertiary amine just stands alone. This bonding magic explains why some amines dissolve in water or boil higher than others. Why do some amines dissolve in water like sugar and others barely budge? It all boils down to hydrogen bonding and chain length. As the alkyl chain, the carbon backbone, gets longer, the molecule becomes less polar and hydrogen bonds can't hold the water as tightly. It's like trying to mix oil and water as the oily part grows bigger. For the same alkyl group, solubility follows this order. Primary amines dissolve the best, then secondary, and tertiary amines trail behind because of their limited hydrogen bonding. Also, bulky alkyl groups act like big bouncers, blocking water molecules from interacting, kind of a chemistry nightclub with a strict guest list. Aromatic amines are even less soluble thanks to resonance that spreads out electrons and lowers polarity. They prefer to hang out in organic solvents. Imagine a graph that shows solubility dropping off as chain length grows. Primary amines start high and tertiary amines pretty low. This helps chemists predict solvent choices when designing drugs or cleaning agents. So, next time you see a molecule, remember, size and bonding shape its solubility story. Dipole moments, the tiny electrical tug-of-war inside molecules, are fascinating in amines. They arise because nitrogen bonded to carbons and hydrogens creates areas of partial positive and negative charges. This charge separation is a vector quantity, meaning it has both magnitude and direction. In amines, tertiary ones surprisingly show higher dipole moments than primary or secondary amines. How? It's all about how these tiny vectors add up or cancel out thanks to the molecule's shape and orientations. But beware, dipole moment trends don't always match boiling points or basicity because geometry can twist these vectors. Aromatic amines like aniline usually have lower dipole moments because resonance spreads out the electron density, reducing charge separation on nitrogen. Picture vectors as arrows pointing in different directions on primary, secondary, and tertiary amines, and their net sum decides the dipole moment. This concept helps explain how molecules interact with electric fields or solvents, essential in everything from sensor technology to drug design. Electrical balance in molecules isn't just fascinating, it's crucial. Time for a boiling point showdown among isomeric amines with the formula C3H9N. We have N-propylamine, a primary amine, isopropylamine, a secondary amine, and trimethylamine, a tertiary amine. The key law here is hydrogen bonding's effect on boiling points. More N-H bonds means stronger hydrogen bonding and higher boiling points. Applying this, the order should be primary amine first, then secondary, and finally tertiary with the lowest boiling point. Simplified, that's N-propylamine boiling highest, followed by isopropylamine, with trimethylamine last. Let's check the data. N-propylamine boils around 48 degrees Celsius, isopropylamine near 32 degrees, and trimethylamine a chilly 3 degrees Celsius. This matches perfectly with the hydrogen bonding theory. Imagine a table showing these boiling points alongside their structural formulas, clearly illustrating how molecular structure governs physical properties. This example wraps up the story. Understanding bonding and structure unlocks the behavior of molecules. Let's wrap things up with the key takeaways on amines' physical properties. First, the boiling point order follows primary amines boiling highest, then secondary, and tertiary amines last, thanks to hydrogen bonding differences. Likewise, solubility in water decreases from primary to tertiary amines for the same alkyl group, reflecting their hydrogen bonding capabilities. The dipole moment, represented as the sum of individual dipole vectors, doesn't always track the same pattern because molecular geometry plays tricks on the net polarity. And finally, hydrogen bonding is present in primary and secondary amines but notably absent in tertiary amines, shaping many of their physical behaviors. These principles guide chemists in predicting how amines behave in water, solvents, or as intermediates in synthesis. That's the beauty of chemistry. Simple bonds explain complex properties. Physics may have apples falling, but amines have us fascinated with their states, bonds, and boiling points. That's it for today's chemistry journey. Keep laughing, keep learning, and see you in the next lesson.